I saw my computer doing crazy things over the director's shoulder, but it seems to be back now. Hopefully it doesn't do that again. Okay, well, it's a pleasure to be here. I grew up in the sort of inner orbit of New York City, and so I feel like I'm in the general vicinity of the home area, and so it is nice to be here. So I'm going to tell you a story about how observations of exploding stars called supernovae revealed to us about 15 years ago that we live in a universe that is not just expanding, but actually accelerating, expanding faster and faster, propelled by a mysterious new component of the universe that we call dark energy. But before I get to the exciting current cutting-edge knowledge, I'm going to take a step back and remind you what we knew of the universe more than 15 years ago to put this discovery in context. So here's an image of the universe. This is actually the deepest image ever taken of the universe. This was taken with the Hubble Space Telescope using its advanced camera, and just picking one blank part of the sky and keeping the shutter open for a couple of months so that you could observe the very faintest things that you could see. And what you see are tens of thousands of galaxies, and that's just in a very small spot. This spot is so small, if you took a single grain of sand and held it out at arm's length, you would cover a spot this size. So the universe obviously is chock full of these galaxies. Some of the faintest ones are 1 trillion times fainter than anything you can see with your naked eye. And when you look at an image like this of the universe, it makes you think the universe is static. You don't see any motion. We kept the shutter open for months, but nothing looks blurry as a result of that. But that's actually a false impression. In reality, the universe is expanding as though it received a big kick that we call the Big Bang, and now the separation between galaxies grows. You could think of this as sort of a cosmic loaf of raisin bread, where the galaxies are like raisins, and over time, the loaf is stretching. The more distant raisins or more distant galaxies appear to move away from each other fastest because there's more space or more dough between us and them. So how do we really know that our universe is expanding? Well, the answer is that we checked. Actually, all the results in this talk we've checked, so I just don't want you to think I'm just making these things up. But really, how is it that we could check such a thing, that the universe is expanding? Well, if you remember back to that animation I showed you, the key was to be able to see that galaxies are indeed far away from us and that they are moving, they appear to be moving away from us faster and faster as you look further and further out. That's what it means for the universe to be expanding. And so we're going to need to be able to measure the distances to galaxies and the speed at which they appear to be rushing away from us. So how do we measure distances in the universe? You might ask, how do we measure distances anywhere, like here on Earth? That's a good place to start our contemplation. Here on Earth, we use a bunch of different techniques. One of them is parallax. This is what surveyors use. If you see a surveying crew out and they're trying to measure the distance to a tree, they might sight that tree relative to an even more distant mountain or something. And then they move their equipment and see how the angle changes between the tree and the distant mountain. They measure that angle, they measure their baseline, they do a little geometry, and they've measured the distance to a tree despite never having walked over to the tree. Another way we measure distances here on Earth is with objects like lighthouses. So a ship captain at night tries to avoid hitting the rocky shore, and as long as the lighthouse looks very faint, he or she knows she's still very far away from shore. That's because captains know that lighthouses are intrinsically very luminous. So for them to look very faint must mean that you're very far away. On the other hand, you could be fooled if, for example, it were a foggy night and you were very close to the lighthouse, but the fog absorbed or attenuated the light from the lighthouse. It could fool you into thinking you're still very far away. But we have other ways of measuring the attenuation over distance besides light. For example, foghorns. Again, we know foghorns are intrinsically very loud, and so when they sound quiet, we know that we're still quite far away. Another way we have of measuring distances here on Earth are to use what I call objects of known size. So you look at a distant object and you recognize it to have a certain physical size, and then the smallness of it, the small angular size, tells you it's far away. When you look at a squadron of airplanes like this, you understand and recognize that these small airplanes are really like the full-sized airplane here, just further away. They're not actually baby airplanes, for example, that were given birth by these airplanes. And so we use these tools all the time without putting a lot of thought into this. So in space, we have to use the tools that are available out there. They are generally not this same set of objects because these objects are mostly human-made. So we have to use whatever occurs naturally in space as well as telescopes to see them. So it turns out one of our favorite techniques is very similar to the lighthouses technique, except instead of using a lighthouse, we use a single star called a supernova that lives in a galaxy like this of maybe 100 billion stars. And at the end of its life, a supernova can explode and be extremely luminous. So here is, whoops, that didn't, let me try that one more time. Here, there we go, is a single star exploding, and it's very luminous. It can be as bright as 10 billion suns. And so when we see one very far away, we can determine how far away it is by the inverse square law. Just like we did with the lighthouse, the brightness declines as 1 over the distance squared. So if it's twice as far away, it's 4 times as faint. If it's 3 times as far away, it's 9 times as faint. And so this is a very powerful way to measure distances across space. Now, once we see one of these supernovae, we can measure its distance, and we can also measure the other property we need to measure to see that the universe is expanding. The fact that it looks like galaxies are rushing away from us. Supernovae, or galaxies, or anything in the universe, emits light. And it emits light at certain wavelengths we're familiar with by determining those in our laboratory. And then, because of the expansion of space, that light is stretched as it propagates to our observatory. So by the time we receive that light, it is redder light. It is what we call redshifted. You may be familiar with the Doppler shift, which is a similar phenomenon where you often may hear sounds stretched, the wavelengths of sound stretched by the motion of the emitter. In this case, it's not actually the motion of the emitter, it is actually the expansion of space itself, which is giving you a longer wavelength of light, and longer wavelengths of light look redder. And so we can measure this redshift, which tells us what the apparent motion away from us is, although it's really, as I said, due to the expansion. So every time we can see one of these standard candles, we can immediately measure how far away it is and how fast it looks like it's moving away from us. And from those two things, we can now get very quantitative. So here's the animation I showed you before of an expanding universe. And so we can look at each of these galaxies, and we can measure its distance and this apparent motion away from us. And seeing a linear relationship between the two is the signature of an expanding universe. It means that these galaxies are not just moving in random directions, they are actually embedded in space in a way that causes them to become further and further away from us as space expands. This is known quantitatively as Hubble's law, and we can measure the expansion rate of the universe by measuring the slope of this line. If the universe were expanding faster, it would be a steeper slope. If it were expanding slower, it would be a shallow slope. If the universe were contracting instead of expanding, it would actually be a negative slope, and we would see mostly blue shifts of the galaxies, not red shifts. Now, this is not just a thought experiment. This was first witnessed by the famous American astronomer Edwin Hubble back in 1929. He was using the 100-inch telescope, and he combined measurements of the redshifts of the nearest galaxies, measured by Vesto Slipher, with his own measurements of distances. And although the measurements were very rough, he could see this linear relationship between the two. In case you have any doubt based on just data like this, when we improve such measurements, and this is, for example, from my thesis, measuring distances with supernovae, you can see a very clear signature of an expanding universe. Hubble's original measurements would fit in this tiny little red square down here in the corner. So you can see we've been able to go much further out and witness the expansion of the universe further out. So now that we know and understand in this talk that the universe is expanding, we can immediately address really profound questions like, when did this all begin? When did the universe start? The reason is because by knowing that the universe is expanding at a certain rate, which we measure, here are all the galaxies rushing away from us and us away from them, we could imagine turning that movie backwards so that instead of rushing apart at the expansion rate that we measure for the universe, imagine that all the galaxies are rushing together at that rate and we're running time backwards. And then the question is, how long would we have to run that movie backwards until everything was back on top of everything else? And that is a measurement of the age of the universe. And so by measuring the expansion rate today, we get a pretty good guess about how old the universe is. For the physicists in the audience, you may notice that the correct units are the inverse of the expansion rate, or units of time, that tell us approximately, to first order, assuming nothing's changed in the intervening time, how old the universe is. Now, when Edwin Hubble made his initial measurements of the expansion rate of the universe, the implied age of the universe was a ridiculously small number. It was only about 2 billion years old. Well, even in 1929, we knew there were rocks on the Earth that were older than 2 billion years. So there was clearly, it was going to be quite challenging to be able to measure the expansion rate of the universe. But as time went on, we got better. We learned more things about the universe, about the objects in the universe. Our technology got better, and as we continued to work on this endeavor, the measurements got more accurate and precise. So here is an article from the New York Times about 2 years ago, The Quest to Measure the Hubble Constant. So here's Hubble's initial measurements up here, but over time the measurements came down as we learned that there were more than one population of stars. We developed better detectors for measuring. The Hubble Space Telescope was launched. We learned to measure distances to supernovae. And in fact, this is just the last couple decades of measurements. And you can see that we have really refined this to the point that the most recent measurement, and this is one that I made with my team using the Hubble Space Telescope, and it's something I'm going to talk about tomorrow in the technical lecture, has allowed us to measure the expansion rate to just about 3.5%. So that has told us that we live in a very old universe, one that's more like 13.5 billion years old, comfortably older than the oldest objects in the universe. So we've learned that the universe is expanding. We've learned that we can tell how old the universe is. But you might wonder, what happens next? What is the fate of an expanding universe? This is very analogous to asking the question, as Isaac Newton did, what is the fate of a cannonball if I fire it off a tall mountain on the Earth? And the answer is, it depends how fast you fire the cannonball, and it depends how massive the Earth is. Because if you fire the cannonball very fast, or the Earth is not very massive, then instead of falling back to the Earth, you could actually send that cannonball into orbit, or out of orbit to escape the Earth's gravitational pull, out to infinity. We call that velocity escape velocity. And so the question is, for our universe, since it's expanding, does it have escape velocity from itself? In this case, the mass is the mass of the universe, and the expansion is like the velocity of the cannonball. And so that was a very profound question that cosmologists struggled with for many decades throughout the 20th century. Now, even before they struggled with measuring this, there was another idea put in place by, of course, the most famous probably scientist in the world, Einstein, who in 1916 had developed a new theory of gravity. Now, Einstein was under the mistaken impression, given to him by astronomers of the day, that the universe was not expanding, that it was probably static, not expanding, not contracting. This was about a decade before Hubble made the discovery that the universe was expanding. And Einstein was troubled by this, because if the universe were static, and then gravity pulled on objects, it wouldn't stay static. The objects would start pulling on each other, and once starting out static, the universe would tend to collapse. And so he was looking for a way out, some kind of loophole, and he found one. He was actually an amazing discovery. In his theory of gravity, although the gravity of objects in the universe is attractive, the gravity of the empty space itself between the objects could be repulsive. He called the gravity of empty space the cosmological constant. Today we would call it dark energy. And he imagined that there was a perfect balance between the repulsive gravity of space and the attractive gravity of stuff in the universe. He thought this until, of course, 10 years later, when he went to visit Edwin Hubble. Here is Einstein, here's Hubble at the Mount Wilson Observatory. This is one of my favorite pictures. This is Einstein. Hubble is proving to him that the universe is really expanding by having Einstein look through the telescope. This must be a PR shot, because even in those days, you could only see the objects Hubble was looking at by exposing a photographic plate for an hour. So there's no way Einstein is seeing anything, actually. But he's a theorist, so he may not know that and may be afraid to speak up. But anyway, in 1931, Einstein acknowledges that the universe is expanding and decided that this whole idea of dark energy was unnecessary and ugly, and he refuted it. So how can we then actually measure if the expansion of the universe is slowing down enough to stop the expansion? Again, like the cannonball that you fire from the Earth, you could measure the cannonball decelerating, and by doing that, weigh the Earth and figure out whether the cannonball was going to escape the Earth's gravitational pull. Well, in the case of the cannonball, you literally can wait and watch and make repeated measurements. In the case of the economy, if you want to see if it's slowing down, you can wait till next quarter. But the universe evolves very slowly, and so we cannot use that trick. We have to use a different trick. And the trick we use is just the recognition that the universe does not instant message. Unlike your smartphones and whatnot, where it feels like you're instant messaging, the universe, it's very clear, gives us very delayed information. So, for example, here is a standard candle, a type supernova, and because it's a billion light years away, we are getting information about it that is essentially a billion years old. This is telling us not how fast the universe is expanding today, but how fast the universe was expanding a long time ago. We could then look for a standard candle that's 2 billion light years away and look even further back in time and tell how fast the universe was expanding even further back. And in this way, by looking out, we're looking back in time, and we can map the expansion history of the universe and figure out if the expansion rate is slowing, and if so, how much. So by the mid-1990s, the expectation was that the universe resembled the model either on the left or on the right. Either the universe was a heavyweight universe, chock full of matter, and was strongly slowing or decelerating the expansion, and the universe would fall back on itself, like the cannonball being launched from a very massive planet that is unable to reach orbit or beyond and just falls back to the Earth. And so the universe would end in something like the reverse of the Big Bang, something like the Big Crunch. Or at the other extreme would be a very lightweight universe, very little matter in it, very little deceleration. The fact that the universe was expanding as fast as it was would mean that it would expand forever. It would reach, it did have escape velocity and would eventually reach essentially infinity. Or it could have been the knife edge case, that we were right in between these, that the universe would exactly reach infinity just as it essentially stopped expanding. That is, the universe had exactly that escape velocity. And so we thought by looking for very distant supernovae in the past, we can map out this past expansion history and see whether it was strongly decelerating, hence heavy and a big crunch, or lightly decelerating, hence lightweight and expand forever. Now, it turns out not any kind of supernova explosion will do. There are different ways stars explode, but there's one very special way that the Indian astrophysicist Chandrasekhar had explained back in the 1930s. And basically, it involves a small star called a white dwarf, very compact. It's really the ember, the inner part of a star that has already gone through its whole life cycle, and lives in a binary. That is, there is a second star that orbits around the first star. And if these stars come close together, material can be transferred or pulled off of this star onto the other star. Now, Chandrasekhar showed that a star like this is only stable up to a certain mass, known as the Chandrasekhar limit, 1.4 times the mass of our sun. And if this white dwarf star should be so unlucky as to collect a total mass of more than 1.4, an immediate runaway thermonuclear explosion will occur on the white dwarf star as it's unable to hold back gravity, and all the remaining elements are fused and a great amount of energy is released. So much energy, it would be as bright as about 4 billion suns, could be seen halfway across the universe. The wonderful thing about this kind of a supernova, called a type 1a supernova, is that when these explode, they're all at just about the exact same mass. So they're like a standard bomb that nature makes. And so when we see one far away, we know that these are great lighthouses, as though you had a set of lighthouses that were all manufactured to the same specification and spread throughout the universe. These provide an excellent way to measure distances in the universe. So the next question is, how do we find these supernovae? These are 4 supernovae that I collected in my thesis in 1995. And as you can see, it's really quite simple. You look at images, and you look for the bright dots at the ends of arrows, and you always find a supernova at the end of an arrow. No, we add the arrows later in Photoshop. The truth is, we have to find them by searching a lot of sort of haystacks to find needles. That is, type 1a supernovae are pretty rare. There's only one in a galaxy like ours about every 100 years. So if you picked your favorite galaxy and just stared at it, you'd have to stare at it probably 100 years before you'd find one. That would be a tough doctoral thesis. You're much better off picking, let's say, 100 galaxies and staring at them all year. Then you'll probably find one in a year, or you get the idea, stare at 1,000 galaxies all year and you'll find 10 supernovae. So you need to look at a lot of galaxies at the same time, but telescopes and modern detectors are very good at this, and so we can image large swaths of the sky and then repeat the observation a month later, and then use computers to digitally align and subtract the images, and computers are good at telling us that they found something that doesn't look like noise and can help us identify the presence of a supernova. So in the mid-1990s, my colleagues and I formed a team, the High Z Supernova team. We were cosmologists and experts in supernovae, and we had been measuring how fast the universe was expanding today from supernovae very nearby, those around us that were witnessing the present era of the universe. And we thought we would look for very distant supernovae that could be used to tell us how fast the universe was expanding in the past. And we could see how much it was slowing down. There was another team at another Department of Energy lab, the Lawrence Berkeley National Lab, which was also attempting to make these measurements. So we had a pretty heated competition trying to measure how fast the universe was slowing down and what its ultimate fate was. I was very lucky in the fall of 1997 to be leading the analysis of our team's data. We had collected our first large set of supernovae, and I was trying to determine how massive the universe was based on how much it was decelerating, using a very simple equation that the deceleration of the universe just depends on what the mass of the universe is divided by 2. And the sort of eureka moment was I wrote a computer program that would determine what the deceleration was from the data and then tell me what the mass was. And the special numbers to look at were that the mass was either close to 0, in which case the universe expands forever, or close to 1 or more, in which case the universe is so chock full of matter it will recollapse. So I'm thinking 0 or 1. Is it a 0 or is it a 1? And I ran my computer program and out came it's a negative number. Negative number, that doesn't make any sense. That the universe should either be decelerating a little because of a little matter or a lot because of a lot of matter. And instead, this negative number was really telling me that it wasn't decelerating at all. It was accelerating. So if you change the sign in this equation and you don't know any other physics, you're required to change the sign of this number. So that's what my computer program was telling me. In reality, it was this term, which at first I neglected, Einstein's famous cosmological constant, which could have the opposite effect of normal matter, causing the universe to accelerate because of this different sign here. So a few days later, I thought, I wonder if it could be Einstein's cosmological constant. Here's a few more pages of math in my lab notebook, and came to the conclusion, yes, at what physicists would call sort of 4 sigma evidence that something like Einstein's cosmological constant was present in the data, indeed was required. So I did a lot of cross-checks to look for some kind of problem. I couldn't find one. And then I began a discussion with my team over email. We were spread all over the globe because we had to be available to observe supernovae at different telescopes in different locations. So it's interesting to look at the email dialogue that occurred upon the rest of the team learning what was in our data, largely because I think people get the impression that scientific discoveries are made and trumpets start blaring and the Hallelujah chorus plays and it's glorious and everybody knows it's that moment. But it's really not like that at all. Here's what the email dialogue looked like spread over 4 continents on a particular day when we were first discussing this in 1998. Alex Filipenko, who was a professor at UC Berkeley that I'd gone to work with, wrote the team. Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. My colleague Bruno Leibengut from Germany wrote back, concerning a cosmological constant, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not sure we are getting the right answer. So there's a great deal of nervousness, conservatism, hesitancy, understandable because most discoveries like this turn out to be wrong. My colleague Brian Schmidt in Australia wrote, how confident are we in this result? I find it very perplexing. My thesis advisor, Bob Kirshner, who was on sabbatical in Santa Barbara, wrote, I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant, only to retract it next year. Mark Phillips from Chile wrote, as serious and responsible scientists, we all know that it is far too early to be reaching a firm conclusion about the value of the cosmological constant. Oops, I didn't skip ahead to that. John Tonry in Hawaii wrote, who remembers the detection of the magnetic monopole and other gaps? On the other hand, we should not be shy about getting our results out. Alex Filipenko wrote again, if we are wrong in the end, then so be it. At least we ran in the race. I wrote, having just gotten back from my wedding, just before my honeymoon, a very quick message to the team. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I have, and I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. Alejandro Clocciati from Chile, if Einstein made a mistake with the cosmological constant, why couldn't we? I never quite understood if that was supposed to be reassuring or not. And then my colleague from Chile, Nick Sunsef, wrote, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. And, of course, Nick was right. We published our paper, Observational Evidence from Supernovae for an Accelerating Universe on a Cosmological Constant, and the other team reached the same conclusion at about the same time, so that both of us were saying the same thing, that it looked like the universe was accelerating, and that 70% of it was in the form of dark energy. And as the director said when he introduced me, this was the breakthrough of the year for Science magazine, that even Einstein would have been amazed. Something that he invented and then discarded had come back and was actually the most important component at this point of the universe. So at the time, people scratched their heads to think, why is the universe accelerating? And we're really not sure, but our 3 best guesses are, the first one, as I said, that it is Einstein's cosmological constant. Now, Einstein only wrote some math to describe this. As physicists, we want to understand, what does that mean? What is dark energy? Okay? And through the development of a field called quantum mechanics, we came to understand that even empty space still has energy in it. You cannot remove all the energy from space. And in fact, if you add up all that energy, which we call vacuum energy, it can have exactly the same property. It can have a repulsive gravity that accelerates the universe. The problem is when you add it up, you get an answer that is a 10 with 120 zeros after it, 120 orders of magnitude too large to be what we see, or would even allow the universe to exist, to not accelerate apart right from the beginning. So we're still working on that calculation. It could be that it's a transient kind of dark energy, that it's what we call a field, and it would actually be the potential energy of that field that is temporarily making it look like we have vacuum energy and is temporarily accelerating the universe, but that eventually this will fade away. This would be a field like you could think of the electric field or the magnetic field, or if you know a little cosmology, you might have heard of inflation or the inflation field. This would be a latter-day version of the inflation field, and it would be changing. Yet another possibility is that Einstein's theory is not quite right, that when we try to finally make use of Einstein's theory of general relativity and gravity, but now on the largest scales of the whole universe, there's some problem, there's some flaw, and what we're calling dark energy is really a sign of that flaw. Now, back in 2000, we thought instead of one of these possibilities, it could just be that we're wrong. It could be that for some reason the supernovae have been fooling us, that the idea was that when we see a faraway supernova, that tells us, when we see a dim supernova, that tells us it's far away. But like the fog, like the lighthouse seen through fog, you can get fooled by stuff in the past. And in this case, we worried, what if there was some kind of mysterious dust filling the universe, a kind of screen of dust between galaxies, and it made distant objects look further away, and fooled you into thinking that the universe was accelerating. So here's the idea. We would see a faint supernova, and we think it means that it's far away and that there's dark energy. But instead, faint could mean that it's really nearby, but that there's a lot of dust between us and the supernova, in which case there would be no dark energy. So we worried about an effect like this, or maybe the supernovae, back when the universe was young, were just born fainter, something really tricky like that. However, we realized that there was a difference between the dust hypothesis and the dark energy hypothesis. If we could find even more distant supernovae, ones that were more than 5 billion light years away, then that dimming from dust should just continue. The further you look through the dust, the fainter things are. Whereas the physics told us that dark energy would only be strong currently, that in the past, dark energy would have been weak and the universe would have looked more compact. Distances would have gotten smaller again. And so we thought if we could just find supernovae further than we've ever seen them, we could distinguish between these two possibilities. Well, we needed a more powerful telescope than anything we had used to that point to find supernovae. So here's a little digression on the history of telescopes and how they've gotten more powerful over time. Here's the improvement in sensitivity over the eye versus year of observation. So here is Galileo's first telescope, which gave us almost a factor of 100 improvement in sensitivity over the naked eye. And then over time, the telescopes got bigger, the apertures got larger, we moved them to mountaintops, we got better detectors than our eye, photographic plates, then charge-coupled devices. Then we learned to place telescopes above the blurring effects of the atmosphere. So, for example, as seen from Hubble, here's a supernova and its host galaxy. It's hard to tell them apart since they kind of get blurred together. Here's the same as seen from the Hubble Space Telescope, and you can see the supernova nicely separated from the host galaxy. So if you need to measure the brightness of the supernova to figure out how far away it is, the Hubble Space Telescope is very powerful for this. And then we've been even more lucky that astronauts have returned to the Hubble Space Telescope in recent years to upgrade its cameras and its detectors to give us the most cutting-edge detectors available, which has improved the sensitivity even more. So we used the Hubble Space Telescope over the last decade, particularly from 2002 to 2007, and using it, we were able to, and its new cameras installed by the astronauts, we were able to find 23 of the most distant Type 1a supernovae, all when the universe was less than half its present age. And here are the pictures of the host galaxies of the supernovae, and then again the arrows are back to show you where the supernovae are in the after images. And so these are type 1a supernovae. The only difference is they occurred a long, long time ago and are telling us how fast the universe was expanding a long, long time ago. And indeed confirmed this picture, that the universe is accelerating now. In the beginning, it was decelerating when it was full of matter and more compact. The universe is not filled with dust, but it is filled with these two mysterious components, dark matter and dark energy. That the universe today is expanding about 20% faster than it was just 5 billion years ago. So now it's not just supernovae which have revealed to us that we live in an accelerating universe. Scientists are very conservative, very skeptical, and if that were the only evidence, we would say, well, there's still something weird about those supernovae, just we haven't figured out what it is. But there's about 6 or 7 or maybe 8 independent lines of evidence now that where you observe the universe in a different way and you come to the same conclusion. Like in the beginning of the talk, when I showed you different ways we could determine distances, lighthouses, same-sized objects, foghorns. This is the cosmologist toolkit of foghorns and lighthouses and same-sized objects that all give you the same conclusion. So, as I said, supernovae were the first, but then we saw an effect known as the integrated Sachs-Wolf effect, which is a very complex-sounding name, but it really means that we could see photons of light from the distant universe falling into the gravitational potential wells of clusters of galaxies. They would gain some energy when they climbed out. They should lose that energy when they come back out, but dark energy has been opening or prying apart these potentials, pushing those galaxies apart, and so these photons don't end up losing as much energy when they climb back out as they did when they fell in. This effect demonstrates the universe is 70% dark energy, same answer we get here. Observations of the cosmic microwave background have been used to determine what the total energy and mass in the universe is. The total is, in those units that I described before, 1. But when we go out and survey how much of the universe is in matter, we only get about 30%. That's been done at least 4 different ways. And so, again, there's a missing 70%. That's the same 70% here, the same 70% here. And then more recently, we've seen that the largest clusters of galaxies are becoming ineffective in their ability to pull in new galaxies because dark energy is so strong on those scales it's begun to push out on those clusters of galaxies. And so we've seen the arrested development of the largest clusters, and also we've seen a change in the absolute scale of the universe from the time of the Big Bang to now that tells us that the universe is about 70% in this form of dark energy. So these are very technical things I'll probably talk about in my technical lecture tomorrow, but I just wanted you to get a flavor for the fact that it isn't just one way that we sample the universe. We do it about 5, 6, 7 different ways, and all of these have reached the same conclusion. But ultimately, we know it must be true because we were awarded the Nobel Prize in 2011, and they would never make a mistake in Stockholm. So we had a really wonderful time just a little less than 2 years ago, bringing our whole team out to share the Nobel Prize. And there was a lot of merriment, a lot of champagne drinking. But behind all this merriment and champagne drinking, there's a dark side, as was revealed in this recent episode of The Big Bang Theory.
It's 2 a.m. What are you doing up?
Nobel Prize acceptance ceremony streaming live from Stockholm.
Sure. I want to see what all the scientists are wearing this year.
Look at these men. They've managed to win the top science prize in the world with no more understanding of the quantum underpinnings of the expansion of the early universe than God gave a goose. You should...
Right, no more understanding of the quantum underpinnings of the universe than God gave a goose. That we are guilty as charged. We do not understand at a deep level why the universe is accelerating. We do not understand the nature and the physics of this dark energy. We know it involves understanding the vacuum, and it requires some use of quantum mechanics and quantum theory, and some use of Einstein's general relativity, and right now there is no quantum theory of gravity, and so we're quite a bit at a loss. The glasses half full side of this story is, for the first time in the history of humankind, we have been able to identify what the universe is made out of, and this is what it's made out of. It's really surprising. only about 0.05% of the universe is in the form of planets, and only about 0.5% in stars. And if you add up all the material, gas, stars, and dust, that are made out of the same elements that you see in the periodic table of elements, that's less than 5% of the universe. Everything we would understand is less than 5% of the universe. The stuff we don't understand is 25% dark matter, and even harder to understand, about 70% dark energy. So the glass is half empty side of this is now that we have found most of the universe, it turns out we really don't understand most of it. And so we have a lot of work to do. Fortunately, we got an assist from NASA one more time in 2009. The astronauts, again, put new cameras into the Hubble Space Telescope, and we've been using these already to improve measurements of the expansion rate of the universe and to find more distant supernovae, to improve our knowledge of dark energy, as weak as it is. Just to show you why we're so keen when we get new cameras on Hubble, here is a picture using Hubble's near-infrared camera. This is a special camera that observes light at wavelengths that are redder than anything you can see with your eye. This is very important because when you look at distant objects in the universe, their light has been redshifted so much that you can't see them in the optical or visible part of the spectrum. You have to look in the near-infrared part. So here is a 48-hour exposure with Hubble, and that's with the old near-infrared camera. And here's with the new infrared camera after just 10 hours. So I'm going to jump back and forth, but pick out a faint object that you can either see in the new exposure you couldn't see in the old one, or take one you see in the old exposure and look at how much better you can see it in the new exposure. So that's with 1/5 the time you could see much deeper, and the field of view is 100 times greater for the new camera. So our ability to survey and look for distant supernovae is just so much greater with this new camera. It's, technology really drives this field forward. And then, of course, plans are being laid by NASA and the European equivalent, the European Space Agency, to build essentially a dedicated Hubble Space Telescope in space to study dark energy. This goes under various names and has been picked by various high-level committees as the most important next thing to do in space. And so at present, both the European Space Agency and NASA are planning to do something like this. Particularly interesting wiggle to this story is, if you saw in the newspaper last year, the National Reconnaissance Office, which is the office of the Department of Defense or the CIA that builds or has built Hubble Space Telescopes that point down instead of up. They had about 10 of these, it turns out, and they had 2 extras. So they were going to discard them and asked NASA if they could use them, and it turns out one of them could be used to become this dedicated dark energy studying space telescope. So we're hoping something like that happens. It will give us, we hope, very important clues as to the nature of dark energy, specifically whether it's constant or whether it's changing. That will tell us whether it's a cosmological constant or whether it's one of these transient energy fields, or whether whether it is acts the same on large scales or small scales, which will tell us whether Einstein's theory has a scale-dependent flaw in it or not. But ultimately, we feel like we need to study dark energy because it lies in the critical path to some questions, some very deep questions we still have about the universe. We know it's most of the universe, and it's hard to say we're almost done when we don't understand the biggest part. It's very hard to understand the fate and origin of the universe without understanding dark energy, because its properties still will dictate what the fate and what the origin of the universe was. But I think the reason we're most interested is there are these 2 disparate areas of physics that we do not know how to unify yet. And so if you could find a place or a time or situation where nature is doing physics at that interface, and we can watch and see how nature does it, we hope that we'll get a really valuable clue how to unify, for example, quantum gravity and get a theory like that. It's quite clear we're very far off right now, as I said, 120 orders of magnitude, but we think by continuing to make these kinds of observations, we might get some of the critical clues that we need. So I will end there and take any questions you have. Thank you.
Is there a question?
Yeah, so to the precision of the data, the question was, do we have any intention to look to see if the expansion is isotropic, if it's the same in all directions? So we have collected supernovae all over the sky, and we have looked to see whether we get the same expansion rate in different directions. And to the precision of the data, we do. It does look isotropic after you correct for some known effects, like there's what's called a dipole in the expansion that's due to our motion with respect to the radiation left over from the Big Bang. So you correct for some known motions, and what's left is isotropic. The problem is that it's not a very precise measurement of isotropy, certainly not compared to the cosmic microwave background. So it seems like, for us, a pretty dull tool.
Second row. Question?
Yeah. Yes. Right. Well, it's interesting to look at the two teams because culturally they were very different. One came from the particle physics world, so they were particle physicists who learned about that this measurement would be good to do, but they ran it like a particle physics experiment. The other group were astronomers who had been studying supernovae and realized that they could use those tools to try to make this measurement. So they came from sort of opposite ends and met in the middle using telescopes to do fundamental physics. So that's how they came together. Then I could say more specifically for my team, there were one or two sort of more senior people, and younger people had sort of nucleated around them. So when a couple of these senior people decided to get together to do this, we sort of formed a team then. One large group at Harvard University, one large group in Chile, and then also in Berkeley.
So for dark matter, we know that it is clustered, right? It comes in clumps. What do we know in that respect about the dark energy?
Right, so this gets a little bit so the question is, we know dark matter clusters. We know that it congregates, coalesces where there is luminous matter. What about dark energy? Is it smoothly distributed or is it clumpy as well? And this gets a little bit back to the question about isotropy. It could be a very important clue. If it's a cosmological constant, it should be totally smooth. If it is one of these kind of scalar fields, theory predicts it would be lumpy in sort of a part in 10 to the 5 or a part in 10 to the 6. Unfortunately, our ability to test that is pretty poor because our samples of supernovae are not that large yet. So I would say we don't know to the interesting precision level. Now, having said that, Brookhaven National Lab and a couple of other places are preparing to do a very futuristic survey for supernovae called LSST, where they hope to collect millions of supernovae. And those are the kinds of sample sizes you need to be able to test whether the dark energy is smooth or lumpy to the precision that actually makes it an important test.
Question.
So if dark energy were to fluctuate as a matter in time, wouldn't then would omega also have to fluctuate? Omega couldn't be one then.
As the universe evolves, it expands, and so omega matter, which is defined as the matter density of the universe, is constantly dropping, whereas omega lambda, what we call the density of this dark energy, is increasing because the volume is increasing. And so the sum of these always stays very close to 1. Yeah. Right. That's a great question. Is the universe expanding at a constant acceleration, or is the acceleration changing too? We don't really know. That's exactly the kind of information we would like to get to be able to tell what kind of dark energy is accelerating the universe. So, so this is really a question of there are higher order kinematic terms, and how high can we measure? And so far, we've been able to see that the universe is accelerating now, and it was decelerating in the past. So if you're keeping score, the next kinematic term is called the jerk. It's the jerkiness of the motion. So we have seen a jerkiness of the motion, but to answer really whether it is the acceleration is constant requires more precision than we currently have. Yeah.
A mundane question. You said one supernova per galaxy per 100 years.
Right.
And my question is, how long do they last, and how much do you have to be on your toes to find them?
Oh, that's a great question. So when a supernova goes off, how long does it last, and how much do we need to be on our toes to see it? Let's see. After a supernova explodes, it reaches its peak brightness in about 3 weeks. But that first week or 10 days, it's so faint that we wouldn't be able to detect it. So typically, if you're lucky, if everything's working well and you're observing on all the good nights that you should be, then you are likely to be able to see it a week to 10 days before it reaches its peak. And we really like to be able to catch it before its peak because the peak is one of the few reference points in time that we actually get. So I would say something like that. Now, having said that, physics helps you out because the universe is expanding, just like you may have learned if you took a course in Einstein's special relativity, the expansion gives rise to what's called time dilation. That means that a clock carried by a supernova would appear to run slow compared to our wristwatch clocks. Or, if you had a twin and your twin went out in a rocket ship, they would appear to age more slowly than you. So these supernovae do age more slowly the further away they are, and the effect is quite significant. So the supernovae that I study with the Hubble Space Telescope typically age 2 to 3 times slower than wristwatch time. So that 1 week to 10 days can become, 3 or 4 weeks. And then they sort of fade away over the course of a month or two. And so we want to monitor them for a couple of months to catch the fade away.
That slowdown is also a clock.
The slowdown is also a clock. So you can actually turn this around as an elegant demonstration of Einstein's time dilation. Yeah, so the question really is, okay, you have one number that should be between 0 and 1, and another number that should be between 0 and 1. As one of the numbers starts out close to 1 and drops to 0, and the other starts out at 0 and rises up to 1, what's the odds that we wake up and look out today at the present epoch, and they're both very comparable to each other? They're very similar numbers, and this causes a lot of heartburn in cosmologists, that it seems like quite a coincidence. Another way to say it is the universe just started accelerating about 5 billion years ago, and that's, on the time scale of our Earth, the time scale of us. And yet, it's very likely going to spend hundreds of billions or trillions of years in the future accelerating. Why did we come onto the stage and just notice this just after this switchover occurred? And at this point, I don't think there's really any good answer. I think, this is one of the things that bothers us. It may seem more natural once we understand the mechanism behind dark energy. I mean, I could say that a very different value of dark energy, which or level of dark energy, which would have given you a very different time the switchover occurred, also would not allow the universe to have life in it. So there's a little bit of anthropic arguments that can be brought into bear on this, but not in any very satisfactory way. Anybody else?
Let's thank our speaker again.